So today we're going to look at a certain technique of integration that's called substitution, or sometimes called the substitution method. And essentially what it is that we're undoing the chain rule. So the substitution method is really the undoing of the chain rule. So before I get into what the method is, let's go ahead and refresh a little bit on the chain rule. So the chain rule is used when I take the derivative of a function, and it's used when I take the derivative of a composition of functions. So that is, if I have a function composed of two functions, f of g of x, then when I take the derivative, it is the derivative of the, so remember, outside inside is generally how we say it. So g of x is like the inside function, and f is like the outside function. So it's the derivative of the outside evaluated at the inside times the derivative of the inside. So that's what the chain rule is. Now another way to look at the chain rule is if I had, instead of f's and looking at primes, if I had y as a composition, I can also look at it this way, that the derivative of y with respect to x, this is our Leibniz notation, so that's still saying the same thing as this, since this is y. The derivative of y with respect to x can also be written as the derivative of y with respect to u times the derivative of u with respect to x. Now, we like to look at it this way sometimes because you can think about using the inside thing as u, and then it makes it a little bit easier to take the derivative. We're going to do an example also. But one thing you can think about here also is if you look at this, it kind of looks like you could just cancel out these du's, and notice that you would end up getting dy over dx if you did that. So that's just kind of a way of seeing why that would work. So let's go ahead and do an example. Let's say that I want to take the derivative of x cubed minus 7x. And let's go ahead and raise that to the 11th power. Now I could do this one without using the chain rule, but I would have to expand this whole thing to the 11th power. That would take a while. So I'm going to use the chain rule, and let's go ahead and use this idea, because this is going to help us branch over to the idea of substitution. So let's look at this part here, the x cubed minus 7x. This is like the inside part. You see that? That's like our g of x. It's the inside thing that I'm doing to x. And then the outside thing, what I'm doing next, is the f part, which is to the 11th power. So what we're going to do is we're going to make u the inside part, that g of x part. So u is going to be x cubed minus 7x. And then what I have is that y, okay, so let's go ahead and say that y equal, just so we have this here, y is going to be this thing, x cubed minus 7x to the 11th. Okay, so if u is x cubed minus 7x, then y I could rewrite as u to the 11th, right, since this inside thing is u. Okay, and the reason for doing that is, notice that this is a fairly easy derivative to take the derivative of. This is also easy to take the derivative of, so it's simplifying things a little bit. So notice here that my derivative would be the derivative of y with respect to u. Okay, the derivative of y with respect to u, using the power rule, is 11u to the 10th. Okay, so dy du is 11u to the 10th. Du dx is the derivative of this with respect to x, which again, using the power rule, is 3x squared minus 7, multiplied by du dx. Okay, now to get the final answer, we want to plug back in what u originally was so that I have my answer in terms of x's instead of in terms of a u and in terms of an x. So I see that I have 11, and u was x cubed minus 7x to the 10th, and then I have my 3x squared minus 7. So there's my answer. The derivative of this is this, using the chain rule. Now notice I could have used this concept also, because f prime is really like the derivative of this 11th power. 11, take away 1 to the 10th. Evaluate at g of x, so evaluate, here's my g of x, times the derivative. Notice this 3x squared minus 7 is the derivative of that inside part. Okay, so now that we have a little bit of a refresher on the chain rule. Let's take a look at doing a specific integral. So let's say I wanted to integrate. Let's do cosine of x squared times 2x dx. Okay, so again, remember this integral is really saying what function did I take the derivative of to get this. So I'm hoping that you can see that the chain rule was at play here, because I see not only a composition, right? I see cosine of x squared, that's a composition, but I also see the derivative of the inside thing being multiplied. Just like this part, if I was taking the integral of this, I see a composition, and I see that the derivative of the inside thing is right here. Here's the inside, here's its derivative being multiplied. So it's kind of similar here. All right, so you might be able to just kind of think backwards to what you would have to have started out with in order to get this. And I see that I would have had to start with a sine function, because the derivative of the outside, derivative of sine is cosine. I would have evaluated that at the inside, and then I would have multiplied by the derivative of the inside, but that's this 2x part here. So do you see how this is the answer just by thinking backwards? Right, if I took the derivative, I'd have the derivative of the outside, which is cosine, evaluated at the inside, times the derivative of the inside, which is 2x. There's what I started out with. Okay, now it's a little tricky sometimes to think backwards. It's okay if that was a little bit difficult. We should probably have a better technique besides just thinking backwards. So let's do kind of what we did up here. Let's think about u being that inside function part. So I'm going to make this x squared. Let's make that u. So u equals x squared. Now I also have this 2x dx part that I'm going to need to get rid of. So let's go ahead and take the derivative of both sides with respect to x. So the derivative of u with respect to x would be 2x. Now I know we always tell you guys not to think of these as fractions, although I did mention it up here as well. But you can kind of think about multiplying both sides by dx here to undo this denominator. And then I get that du is 2x dx. And that allows me to replace this with a u and replace this with a u. So essentially what I have after I do that is I have a new integral. Okay, I have cosine still, that hasn't changed, but now I'm saying that u is x squared. So I can say that's cosine of u. And this 2x dx, that's just du. Okay, so the whole point of doing that is, let's take a look at what we have here. This is kind of complicated, right? We weren't quite sure how to deal with that. But look at this one. This is something that we already know how to take the integral of. So this is much easier for us to work with. Okay, so let's go ahead and finish this. Let's find the antiderivative. So the antiderivative of cosine of u with respect to u would be sine of u. And remember that since this is a general antiderivative, or the indefinite integral, I should have a plus c there, plus some constant. But just like up here, I didn't want to leave my u. I want to get it back in terms of x. So let's plug what x was back in here. U is x squared. And notice that's my answer that I also got when I just kind of tried to intuitively think backwards, which isn't always easy to do. Okay, so again, what we did is we picked a u, and I picked this to be u because, one, it's an inside part. So I see that's kind of like my inside part for a chain rule. But also, I see its derivative in here. So that's making me kind of realize that that should be what I pick u as. Let's try another one, try another example. Okay, so let's look at the integral of 3x squared times the square root of x cubed plus 4 with respect to x. Okay, now I'd recommend with this one, well, let's start off with seeing that we have a composition here. So here I see that I have the square root of a function. So that means that this is like the inside part, because that's the first thing I do. And then I take the square root, so that's the outside part. So I see a composition. Not only that, but I see that I have the inside part and its derivative being multiplied. Sometimes it's easier to see that when we rewrite it. So feel free to rewrite this if you'd like, times 3x squared dx. Now what I'd like you to do is use this same procedure. Okay, go ahead and pause the video, use the same procedure here to figure out what the antiderivative is, and then I'll go over it and you can see if you have the right answer. Okay, so let's check out what the answer is. So I mentioned that this was the inside part and this is the outside part. So let's make u the inside piece. U is x cubed plus 4. So instead of writing du divided by dx here and then multiplying both sides, I'm going to skip a little step here. Du over dx would be 3x squared, right? The derivative of x cubed. Derivative of 4 is 0. So instead of dividing by the dx here, I'm going to think about multiplying by both sides, like we did here, just to automatically get to this step. Okay, so I have that this part is u, this part is du. So let's just look at how much that simplifies the integration process. So now I have the square root of u du. Notice that is much easier than the integral that we started out with. Okay, so that's a good sign. Now to take the integral of this, I can see that this is going to be a power rule for integrals. So let's write this as u to the 1/2. And now we'll use the power rule. So I have u to the 1/2 plus 1. 1/2 plus 1 is 3/2 divided by 1/2 plus 1 plus that constant. Okay, so let's just simplify this. Dividing by 3/2 is the same as multiplying by 2/3. And I'm still not quite done because I want my integral to be in terms of x. So we will again plug in what x was, or I guess what u was. U was x cubed plus 4 to the 3/2 plus c. Now the beauty of integration is that you can always check your answer by taking the derivative. So think about taking the derivative of this. I'm just going to kind of talk it through, but feel free to write it out on paper. I'd use the chain rule. So what I do is I take the derivative of the outside function, which would be bringing the 3/2 down. Notice that cancels with the 2/3. My new power would be this minus 1, so 1/2. So I essentially have this part gone. This would be the 1/2 power. Then I'd still have this same inside part, x cubed plus 4, times the derivative of that, which is 3x squared. Notice that's what I have here. This to the 1/2 power, then the derivative, which is 3x squared. So you can always check your answer by taking the derivative. Okay, now let's do a really similar one. I'm just going to think about taking away that 3. So let's say we have this instead. Okay, so no more 3. Getting rid of that. So it's still a similar question, or a similar integral, but it doesn't seem quite as simple because I have an inside function, but I don't have exactly its derivative being multiplied. That is, it's not 3x squared, the exact derivative, but it's kind of like it. So let's go ahead and see how we can deal with this. So let's make this part the u part again, because it's still the inside piece. X cubed plus 4, and then du is then going to be 3x squared. And don't forget this dx part here. It's really important that you have that there, because you'll need to replace this dx part right here. Okay, now I'm going to go ahead and rewrite this again, just so I have everything in kind of the order that I want. So I have square root x cubed plus 4, and then we'll write x squared dx. Okay, so again, I have an x squared dx, but not a 3x squared dx. So what we can do is basically try to get this right side to match exactly what we have here. And I can do that by multiplying both sides by 1/3. Or you can think of dividing both sides by 3, right, to get rid of that 3. So I see that 1/3 du is x squared dx. So that allows me then to replace this u and to replace this with not du, but 1/3 du. 1/3 du is x squared dx, that piece there. Okay, so that means then that I have the integral of square root u times 1/3 du. Now remember that if I have a constant multiple, I can pull that in front. So that means that I really have 1/3 integral square root u du. And I'm actually going to stop right here because I see that I'm going to have the exact same answer that I had before, except this 1/3 is now out in front, right? The integral of square root u du, we did that right here. And here's the answer that we got. So the only difference now is that I want to multiply the end result by 1/3. And so I get 2/9. Now notice you would have to distribute this 1/3, but 1/3 c and c, I mean, either way it's still a constant. So either way you'd like it, you can put a 1/3 here, or you can just leave it as it is, that's fine. Okay, so all of those are examples of looking at the indefinite integral. So let's take a look at if we have instead the definite integral. So let's take a look at the, get centered here, the integral from 0 to pi over 4. Let's do secant squared times tangent dx. Now the thing about this one is it's not quite as obvious as far as a composition goes, but let's just think about whether we see a function and its derivative. Okay, so I see that I have tangent, and I know that its derivative is secant squared. So just with that in mind, that's a good place to start as far as u substitution goes. If you see a function and its derivative, make the function u. Okay, so I see I want u to be tangent, and I see that du then is secant squared. And you could either reorder things, or you can also say that this and this together is du, because du is secant squared x dx. So let's rewrite this. I have the integral of, okay, so again, this part's u, tangent is u, and then this whole thing is du. So after I've replaced everything, I just have the integral of u du, which again is much simpler than the thing that I had started out with. But what I want us to think about now is what the bounds should be here. Okay, should it be, again, from 0 to pi over 4? Now, this is saying that the x values, right, x, is ranging from 0 to pi over 4. But now I have it in terms of u, and u is not ranging from 0 to pi over 4. So to change the bounds, I really need to look at what is u when x is 0, and what is u when x is pi over 4. Okay, so do you see that? Because this is in terms of x, and I need to now change it so that this one is in terms of u, so that my variables and my bounds match one another. So let's find that. U of 0, again, x is 0, I want to figure out what u is. So tangent of 0, might remember that one as being 0. And then u of pi over 4 is tangent of pi over 4, which is 1. Okay, so the way I'm getting these is, if you remember, the tangent function essentially tells you the slope at wherever your angle is. So this would be an angle of 0. I can see the slope, it's a horizontal line, so the slope is 0. This one is an angle of pi over 4. And I can see the slope, the x and y are changing at the same rate, so the slope is 1. You can also get those in your calculator. Okay, so my new bounds then are integral from 0 to 1 of u du. Now again, let's just take a look at what we have over here. We have something in terms of secants and tangents and pi, and here we have something as simple as just the integral from 0 to 1 of u. Much easier to work with. That's kind of the main idea here behind the substitution method, is really just making life easier, making integration easier. So visually, how I want you to think about this is, if I were to look at the graph of this first integral, okay, so if I look at the graph of secant squared x tangent x from 0 to pi over 4, feel free to do this in your calculator if you want to look at what it is. At 0, it's, at 0, it's 0. Tangent of 0 is 0. And at pi over 4, it would be 2. And just graphically, it looks like this. This isn't something that I would expect you to know the shape of. It should be a little more curved than that, but you kind of get the idea, a little bit more curvature. So what I'm looking at then is this area here. Now, I have also then this other definite integral, definite integral, and if I graph the equation u, well, that would be like kind of like the equation y equals x. You know, here's my u-axis. It would be like that. And I'm graphing it from 0 to 1. That would be 1, and that would be 1. So I'm looking at this area. Now, I can already see just by looking at this that the area should be 1/2, right? The whole thing would be 1. This part would be then 1/2. Okay, and then think about this piece also. If I think about making a square here, it would be 2 times, or I guess this length would be pi over 4 times 2, which would be pi over 2. It's a little bit more than half of that. This area is also exactly 1/2. It's not quite as obvious as this one, but it is. So essentially what I've done is I've taken an integral, a definite integral, and made it look like another definite integral that has an easier area. So these have equivalent areas. Okay, so let's go ahead and finish this one, although I do see again I should get 1/2. Let's go ahead and use the fundamental theorem of calculus. So I have the integral of u is 1/2 u squared. Evaluate that from 0 to 1. Plug in 1, so 1 squared, minus plugging in 0, which would just be 0. And there's that 1/2. Now notice that my bounds here are still 0 to 1. I still have it in terms of u. And in the other examples, I've said make sure you replace it so it's in terms of x. But since it's a definite integral, I'm going to get a number out. It doesn't matter which number I get, they're equivalent. So if I keep it in terms of u, I should keep the bounds 0 to 1. If you wanted to change it back to x, then my answer would be 1/2 u. U is tangent squared, evaluated from, now it's in terms of x, 0 to pi over 4. But notice what I'm going to do here. I've got the 1/2. I'd take tangent of pi over 4 squared minus plugging in 0. Okay, tangent of 0 is 0, so that part's going to be 0. 0. And tangent of pi over 4, we already did that. It's 1. So I still have 1/2 1 squared. Just like I did there, I still get 1/2. So you don't have to go back and replace it in terms of x if you're looking at a definite integral, because you're going to get a number out anyway, and it's usually easier just to keep it in terms of u. If you're looking at an indefinite integral, you want your answer to be in terms of x, right? Indefinite integral gives a function as the answer, so that's what we want to get.